All right, so we're going to take some notes at the Physics 1 level in how to use VIR charts to solve series and parallel circuits. And in this first lesson, we're going to learn how to work with series circuits. So the first thing you need to know, you kind of need to memorize some rules in the way that voltages, resistances, and currents work when you wire resistors in series. And so we have this statement that some adults view resistances so carelessly. And that is a secret acronym that translates with each letter in the front of the word into statements about series. So the S for some means we're talking about series circuits. And in series circuits, we're going to add voltage drops to get the total voltage drop for the whole circuit, which comes from the battery. And then we're going to add the resistances for each resistor to get the total resistance. And then the so means we're going to have the same, and the same what? The same current is going to flow through each resistor that's wired in series. So we need to memorize this. Now we're going to go ahead and apply it. And so let's make up something to apply this to. So let's just say, yeah, Alex? Right. Let's just say, for example, that we have some components. So we're going to say that we have, and components is just a fancy word for parts. And parts of a circuit. So let's say that we have 3 light bulbs. So we have 3 light bulbs, 3 bulbs. And the light bulbs have a property that is going to be the same no matter which way you wire them. And that property is their resistance. And so that's why they're called resistors, because they'll have the same resistance no matter how you wire them. And so let's say that light bulb 1, we'll call it resistor 1, or with a little subscript 1. And it has a resistance, no matter which way you wire it, of 1 ohm. And then light bulb 2 we'll call R2, and it has a resistance of 2 ohms, and light bulb 3 has a resistance of 3 ohms. We'll just keep the numbers simple for our first example. And then we're going to also have a 9-volt battery. You know those like rectangular shaped batteries that have the wide and the skinny nub on it? Yeah, so we're going to use one of those 9-volt batteries for our circuit. So we're going to have a battery, and it's going to equal 9 volts. So those are our components. And then we have a bunch of wire laying around, maybe alligator clips, and we can clip all these things together. So let's go ahead and wire these up in series. So then let's make a series circuit. Let's wire them in series, and that would look like this. Your battery is going to be a long and a short parallel lines. And the long line represents the positive terminal of the battery, and the short line represents the negative terminal of the battery, and the positive terminal is where you have the highest voltage. You would have positive 9 volts at the positive terminal, and then you'd have 0 volts at the negative terminal. You'd have the lowest voltage there. And then we're going to connect it with wires, so we're going to run these wires off of here. And then we're going to wire these in series. So each time you draw a squiggly line, that's a resistor. Then draw some more wire, another squiggly line. And we have 3 resistors, so we're going to need one more squiggly line before we get back to the battery. So there's our 3 resistors. Now, you don't have to draw this next picture, but I just want to show you, to kind of expand your mind, I want to show you that another drawing that's exactly the same as this one to the circuit. So here's our battery again. What if we just did a long piece of wire and then ran it around and had a resistor there, and another resistor there, and another resistor there, and then ran it back to the battery? That would be exactly the same thing to the battery as the first one. It doesn't look visually the same as our picture, but they're all 3 wired in series, one right after the other. There's a single path for the current. The current's going to flow in the same direction. We just made one piece of wire look longer than it did in the previous picture. So you're going to keep your mind open to that and look for just, the thing about series is, you can look at S for series, and you can say that there's an S for it gives you a single path. And P for parallel, and as we'll see in our lesson tomorrow, P for parallel, P for plural paths, or many paths. And so we have a single path for the current here and here as well. We'll just go around in a loop like that. Now I'm going to get rid of this picture because I'm going to use this space to do a VIR chart. So we're going to go back to Molly's favorite color of blue, and we're going to make a big square. Take up a lot of space with this on your paper. Give yourself a lavish amount of space. And then on the far side, make one thin column and make a thin row across the top. And inside that thin row across the top, write Ohm's law, which is V equals I times R. Save yourself a little bit of space on the right-hand side, and then make another column. And in that column, make the line separating it really thick, because we're going to ignore this right-hand column until we're all done with the VIR part. Now we're going to make some rows in our VIR chart. And so the rows are going to be, we're going to make one row for each resistor. And so let's name these resistors. And so we had resistor 1, R1, and that was equal to 1 ohm. And then we had resistor 2, we'll call it R2. That's my favorite one because of R2D2. And then we'll have resistor 3, R3, and that's 3 ohms. And so let's make a row for each of those, and then we'll make a row for the battery. So for the battery, all right, so here we go. R1, R2, R3, and then battery, I'm just going to write BATT because I don't have the space for the whole word battery. Then make your lines for your rows. And then let's make columns. Make a column for each letter in VIR. For the voltage drops, for the currents, and the resistances. Oh, got a phone call. Hutcheson. I do. Sure. All right, you're welcome. Bye. All right, Donald, you're being dismissed, buddy. Maybe you can check this out later and you'll get the rest of it. So let's fill in what we're given. You know how we talked about the guess method, GUESS, givens, unknowns, equations, substitute, solve? The VIR chart gives us all that in one place. So we list our givens inside the chart. The missing spaces are the unknowns. And then the equation is VIR across the top. And then we can substitute and solve as we go through. So let's list our outer givens. So for R1, R2, and R3, we know the resistances for all of those. So just line that up with the resistors column. So R1 has 1 ohm of resistance, R2 has 2 ohms of resistance, R3 has 3 ohms of resistance, and then we also know the voltage of the battery. We said we're going to use a 9-volt battery, so we can go over to the battery row, and in the voltage column, we can put 9 volts. Okay, now I've put all my givens in the chart in this blue, and I'm going to switch colors to indicate the things that I have to go searching for. So let's use maybe this nice yellow color here. And these are going to be, all the yellow things are going to be things we had to go find. So let's go back to our rules. So in series is going to add voltage drops and resistances. And that's what I want to play with now. Let's look at how series adds resistances to get the total. So let's go back down into our chart. And let's add the resistances together to get the total resistance. So we just do 1 plus 2 is 3, and 3 plus 3 is 6. And so we get a total resistance of 6 ohms. Now that wouldn't work that way if we wired in parallel, but because we memorize our thing about series, it works that way. Now, there's kind of a game you're playing. The game is to collect 2 in each row. If you collect a V and an I, or an I and an R, or a V and an R, then you can use VIR to solve for the missing piece. So what I mean by that is, here we have in the bottom row, in the battery row, we have 9 volts, and that's our V. That equals some current I times 6 ohms of resistance. So now we can use VIR to solve for that missing piece. And so it's kind of a collect 2 to unlock the third in each row. And so let's do that. Let's kind of do, we have 9, here we go. We have 9 volts equals I, and that's going to be times 6 ohms of resistance. And then to solve for I, just divide both sides by 6 ohms. 6 ohms cancel on the right-hand side. 9 divided by 6 is 1.5. And that's going to be equal to I. And the unit for I, the unit for current, is amperes. And so we use a capital A because it's named after someone. And so we capitalize it in honor of them. Now we can fill that in our chart. 1.5 capital A amps. Now if you look at our chart, we're kind of stuck because we don't have 2 in any other row. So when you get stuck and you can't use VIR, go back to your memorized statement about series and see if you can find anything that connects. Let's go back and let's see. So we just used the fact that in series, you're going to add your resistances together. Now, if we had voltage drops, we could add them together, but we don't. We only have the total, so we can't do anything there. But we do have the last thing there. The last thing says that in series, everything wired in series is going to have the same amount of current flowing through it. And that is beautiful. That's huge because if you unlock the current anywhere, you unlock the current everywhere. So to indicate that, I would just highlight this column as a note to myself that everybody in that column is going to have the same value. And that happens because they're wired in series. So I unlock the 1.5 amps, and then 1.5 amps of current is going to flow through every single resistor. So that just unlocked a variable in every single row, which now unlocks the voltage. If I just multiply 1.5 times the resistance in every row, I'm using VIR to get the voltage drops. So now I can do 1.5 amps times 1 ohm, and I'll get a voltage drop. Let's use a nice pink color here. I'll get 1.5 volts. And then 1.5 times 2 for R2, and that's going to be 3 volts. And then 1.5 times 3 is 4.5 volts. And you know what? The last thing that we didn't use in our statement that we memorized about series is actually the way that we can double check our work. It's really beautiful in that we go back up to our statement and it says series adds voltage drops. See, we didn't use that piece of knowledge yet. But now we can use that to go back and double check our work. And so we should be able to add up the voltage drops for each resistor, and that should add up to the total that comes from the battery. So let's go and see if that works out. If that works out, that means that we did everything else in the chart correctly, and we don't even need an answer key because we are our own answer key. It's really cool. So we should have 1.5 plus 3 plus 4.5, and that does equal 9. 1.5 plus 3 is 4.5, and then 4.5 plus 4.5 is 9. So it's really awesome. So we were able to double check our work there. Now the last thing we're going to do is I want to ask the question, can I predict the future? Can physics allow me to predict the future? And here's what I want to predict. I want to predict that if I take these 3 light bulbs and I wire them in series, which light bulb is going to be the brightest? Or will they all be the same brightness? I haven't even wired them yet, but can I predict that for the future of the light bulbs? And the answer starts with a Y and ends with an ES. Yes, we can. And here's how. Take your VIR chart and use that last column, turn it into a VIRP chart with a P. And here's what it's going to look like. Let's use a nice light lavender color here for power. P equals I times V. P equals I times V is what we call Joule's law. Joule's law after James Joule. And then we were just using Ohm's law with VIR. And we're going to be able to calculate the power for dissipated by each light bulb. And why would we care about that? Well, it turns out that power is the rate at which that light bulb is converting energy from electrical energy into heat and light. And so if power is greater for one light bulb, it's converting more energy faster and giving us more light. And so it's going to be brighter. So power is connected to brightness. And so let's calculate the power. Just do each row, do I times V. I times V, and I times V, and I times V. And so we do 1.5 times 1.5 for R1, 1.5 times 1.5 equals 2.25, 2.25. And then we do 3 times 1.5, and that's 4.5. And then we do 4.5 times 1.5, and that is 6.75. And then we do 9 times 1.5, and we get 13.5. Now we neglected something. We didn't write the units. So we need the units for power. And we have that little joke, that little pun in physics. Watt's the unit for power? And the physicist says, yes. Watt's the unit for power? Yes, Watt is the unit for power. W-A-T-T for James Watt, the father of the Industrial Revolution. And he made a great improvement on the steam engine. So capital W in honor of James Watt. And that's spelled W-A-T-T. James Watt. Now, which light bulb would be the brightest? And let's kind of just color it here. I'll use so on the actual circuit here. I'm just going to kind of color and highlighter and make it brighter if it would be brighter. So here we have 6.75 watts for R3. So it would be the brightest. Oh, real bright. Thank you.
How many lumens is it?
So many lumens.
How many?
I don't care right now.
But lumens.
But lumens will lumen later. And then R2, 4.5 watts. So it's going to be not quite as bright. Oh.
Why is it? I thought it was one light switch. So there's 3 bulbs.
Yeah.
The resistors are bulbs.
Yeah, the resistors are light bulbs, and they're not all the same light bulb. So they might not shine as brightly as each other, even though they're on the same circuit. Yeah, that was a good question, Patrick. And then 2.25 watts for R1. So that one resistance, that 1 ohm, is going to be like, oh. I mean, it's on, but it's really not that bright because it's not expending as much power. Yeah.
Why is the last one the brightest?
The last one is...
Do you think the one with less resistance would be the brightest?
Okay, good question. Well, here's what matters for brightness. How much energy is being given off every second? So energy is related to the voltage drop and the current flushing through there. All right, and so we have I times V. Now, the current is the same for every resistor there, but because R3 offers more resistance to that current, but the same current has to be pushed through it, it's going to make kind of the equivalent of more electrical friction, which if you had friction with your hands and you rub them together, that would get hotter. That'd be more energy from that heat. And so this is going to give more heat, but also give out more light. And so the higher resistance bulb, when you force the same current through it, is going to drop more energy every second, which is going to give you a bigger voltage drop and give you more power given off. So this, yeah. Now, there's one way to double check our power. You know how we double checked our voltage drops by adding them together to see if they resulted in a total? We can do the same thing with the power. And so because power is just how much energy is given off every second, if it's just like an amount of energy. And so if you have 2.25 amount of energy, 4.5 amount of energy, and 6.75 amount of energy, just adding together all those amounts will give you the total amount of energy given off. So we can double check our work by just adding together all of these powers, and they should equal the total. And that is the case. 2.25 plus 4.5 plus 7.5 equals, or 6.75 equals 13.5 watts. So it's another way to double check our work. All right, now here's your turn. Here's what you're going to do. Let's see if you can come up with the answers to this circuit that I'm going to draw for you. Let's do this in a nice orange color. So now what I'd like you to do is imagine that you have 3 more light bulbs, an R1, an R2, an R3, and you're going to wire them in series, and R1 and 2 are the same light bulb. They have 4 ohms of resistance each. R3 actually has 16 ohms of resistance, And instead of using a 9-volt battery, you're actually going to use a combination of lantern batteries that each have 6 volts, and you're going to use enough of them. So you're going to have a battery that offers 24 volts of potential difference. And I want you to wire them in series.
In total, or?
Yeah. So you can just draw one battery symbol and write that it has 24 volts to it. All right? So now what I'd like you to do is draw a diagram for these 3 bulbs in series, and then make a VIR chart and find out all the things that we found out. And then find out which light bulb will be the brightest using the power. You might find that the math ends up working out nicely for that. So don't be scared that the math works out so nicely. This was built intentionally that way. And then once you complete that one with that nice easy math, let's see if you can take it up a notch and do a series circuit with some 3 different bulbs and a DC source that has the same voltage that American electrical outlets have. Yeah, sure. And so that would be, let's say it's a battery that offers 120 volts. And now your resistors are going to have 20 ohms, 30 ohms, and 40 ohms. And again, wire them in series. And you're working to discover which bulb is brightest.